astronauts to going back, NASA has limits about the amount of ionizing radiation that astronauts can be exposed to over the course of their entire career. And in 2020, they were overhauling their guidelines about what those limits should be, how they should be justified, and how they should be communicated to the astronauts as well as the public. And they asked the national academies to convene a group to help them think through the process and give their evaluation of the final policies that NASA would converge to. It's been a very interesting interactive process. The committee was asked specifically to comment on what you see in the title in yellow, managing and communicating cancer risk. And that's very much the topic of today's talk. There are many other interesting aspects of this venture from a statistical standpoint, particularly the whole issue of estimating cancer risk from ionizing radiation is quite a complex one, and there's a wealth of literature. Some of the references that I gave you would give you the opportunity to dig a little bit deeper into that, but we will not discuss that, in part because the committee was very clearly tasked to do something else, but it was also very clearly stirred back to this something else when we try to make comments about the modeling. Not that this is implied to be a critique. I learned a lot and was very impressed by the modeling that they do at NASA, but I want to focus this presentation on what the report was tasked to do. I already see something in the chat. I wonder if that's me. Let me take a quick look. That is, no, that's not. Yeah, that is, oh, that's my links, but coming in from somebody else as well. Apologies for the interruption. So as a result of this focus on the report, I want to bring up some discussion points that I think for me were the major takeaway point from the perspective of what deeper questions did I walk out of this experience with that as a statistician I really struggled with from a foundational standpoint. And it's a lot of the exercise, as we will see in quite a bit of detail, has to do with risk, but it also has to do with risk estimates that are quite complicated and speculative, and models that present a lot of model uncertainty. NASA does a quite thorough job of modeling and quantifying the uncertainty about risk, and we'll see how they do that, a little bit about how they do that. How does this uncertainty about risk need to, what are the best ways to incorporate this uncertainty about risk in decision making about setting the limits for the exposure, occupational exposures for astronauts? And you will see that this is a topic that was really at the center of what the committee had to evaluate, and it is one where we made a decision, but by no means we're left with a very, very clear guidelines of what is a principal way of thinking about this. And I very much welcome any comments that folks in the audience may have, and I'm hoping to see things pop up in the chat in due time about this comment. A second related question in this context is, given that risk is driving the decisions about how to limit the amount of exposure that astronauts can undergo, which can have severe limitations on what they can or cannot do in their careers, because at some point they run out of brownie points and they stay on Earth. How should these uncertainties be communicated to them, and also how they should they be communicated to the public? So how do we communicate uncertainty about a probability or about a risk? This is a question that we face actually daily in our own work in precision medicine, when we try to understand prognosis for patients, and we do it based on statistical models. And we know that those statistical models are not exact. And very often we also have the ability to put a number or an interval or some notion of uncertainty around the risk predictions that we provide to patients. We struggle enough with communicating the risk, the concept of risk to patient, but we know that the risk number that we give them is itself subject to uncertainties that are epistemically of a different nature, perhaps. How should we communicate those? How do we best communicate those? So that's something that came up very much in this in the work of this committee as well. I'll show you what the final approach is that NASA is going to follow going forward. But again, I welcome comments both in the context of this report as well as more generally in terms of our own work about what is the best way to communicate uncertainty about uncertainty. Last but not least, one of the central issues that the committee had to grapple with had to do with the situation when risk is not the same or is believed to not be the same in different groups. In this case, differs by age and more importantly by gender. And so the question of how to set limits to the exposure, which translate immediately into setting limits to the opportunities that astronauts have to participate in certain missions, comes up in terms of a very difficult dilemma between applying equity to the opportunities that are given to astronauts in the astronaut pool versus leveling the maximum risk that astronauts should be exposed to. So we'll mull over this question as well during the talk. So that's the goal. I will cover, I think, just enough material about the context and the science for us to be able to think about these questions a little bit. And I hope to hear from you about what your thoughts might be. There's an infinite amount of learning that can be done about this subject. And I hope that those of you who are interested will dwell into the links that I provided. If you're a freshman, also you can, or if you're a freshman, you can take my freshman seminar in the spring, where we'll do essentially a version of this talk that will last for the whole semester, and you'll get to check some of those references yourself and bring them to the class and discuss these points. Okay. So I generally start my presentations with a bunch of disclosures, and I think it's I find it a good, healthy way to clear the air from potential conflicts of interest. And there are many now in our field that people don't acknowledge sufficiently. Most of my conflicts have to do with precision medicine, and while they do relate to risk and uncertainty about risk and risk communication in many ways, they are very far removed from the context of this proposal. Perhaps the most relevant disclosure is the one that I need to make at the bottom, which is that I know absolutely nothing about space, about radiation, and about many of the aspects of physics that will be discussed. And I am also, unusually unfamiliar with the context of space exploration for a person living in the Western world. I never even watched a science fiction movie. So it will come as no surprise to you that the most fun part to me of this committee were these arcane philosophical questions that I'm hoping to hear the feedback from you about. So with that, and almost 13 minutes into the hour, let's venture into the material for today. I'm going to show you some pictures and materials that look at the dose of ionizing radiation that astronauts are exposed to, and the limits thereof. These limits are quantified in terms of something called an effective dose. And I've borrowed this cartoon from the Japanese radiation protection website, a website whose link you also have, and it's a very, very basic and accessible discussion of these issues that was put up by the Japanese government following the Fukushima nuclear power accident when one of their nuclear power plants was hit by a tsunami wave. Anyway, this slide is from them, and it illustrates how, at least at a very cartoonish level, how an effective dose is conceptualized. On the far left, you have the dose that is external to the individual being considered. And then the effective dose is the output of this process that tries to quantify the dose that the whole body receives as a result of the exposure. It's essentially a scaled weighted average that looks at each individual organ. Each organ has a weight that reflects how much of the external radiation is typically absorbed by that organ, and there are quite substantial differences from organ to organ. For example, the skin is better at dealing with radiation, as you might imagine, than say the lungs. And then there's an overall scaling factor. The unit of measurement that we will talk a lot about is this unit of sieverts. And actually, we'll talk a lot more about millisieverts with a little lowercase m in front of the SV. And they measure essentially energy per kilo after it's been translated through this process. The energy that's on the outside environment is measured in grays, and it's also essentially joules per kilos, but without a translation in terms of what gets absorbed by the body. This is a model that is used a lot, for example, also by radiologists to try to understand how much radiation overall people receive if they are irradiated at certain organs. But for the purposes of this discussion, it will typically be all of the organs receiving the radiation, and so this model is maybe a little bit of an overkill. But I just thought I would clarify the notation, because you will see often effective dose being used as a scale in some of the figures that we will look at, and sometimes you will also see absorbed or equivalent dose. So those are the millisieverts for you. How does a millisievert relate to our sort of day-to-day experience? This is a slide that I borrowed from the Canadian Nuclear Safety Commission, and it gives you example of a familiar situation where people are exposed to radiation and the corresponding amounts. So you can start at the bottom left. At the bottom left, you see someone going to the dentist and getting an intraoral X-ray, and that's 0.005 millisieverts. If that person now jumps on a plane in Vancouver and flies all the way back to Montreal, then they are exposed to 0.02 millisievert. Then they take a job in the uranium mine in Canada, and over the course of the next year, they get exposed to 1 millisievert. But also, if you just hang out in North America as a result of radiation that comes from the ground and some from the atmosphere, it's just part of the background radiation on Earth, you get exposed to maybe 1 or 2 millisievert, depending on the area you live in, how much radon is in the ground. As you move up this scale, you start getting into space. Let's jump over the energy worker. On the top right, you can see that someone who spends a year in the International Space Station, not many of us, but we're talking about astronauts here, is going to be exposed to about 150 millisieverts. At 1,000 millisieverts, or 1 sievert, is when the exposure to radiation, ionizing radiation, is starting to have acute symptoms. So expanding a little bit more on the astronauts' experience, this is a chart from NASA that is also included in the National Academy's report that looks at data on every astronaut that's ever been in space. Each point represents an astronaut by mission pair. So a point is really a mission, and it's ranked by effective dose. The effective dose, you see it as the little square, and the little squares are close enough to each other to form a long black line. So if you were on the Apollo or the shuttle, you got about 3 or 4 millisievert, which is all things considered not too far from the average dose of a US person, counting the background radiation, the dentist, and everything else that they might do. As you move to the right, you're getting closer to missions that take a much longer time. And for example, you get too close to the 150 millisievert that the Canadians were estimating when you're talking about the International Space Station, Skylab, and so forth. And then the interesting data point here is the outlier on the top right, which is NASA's projection for what a Mars mission would be like. And there's represented by that little orange square. The scale is in the log scale, right? So here we are talking about well over 1,000 millisievert for Mars. So that's by the way of background on what the scales are that we are talking about. So, ionizing radiation is not very good for people, and probably you all know this. What happens when you get zapped by a cosmic ray? If it hits right in the nucleus of your cell, it causes DNA damage. And then in this grossly oversimplified model of reality, one of 3 things happen. One is that the DNA damage is correctly repaired by the DNA repair machinery in the cell. One is that the cell is so severely damaged that it dies. And when a lot of that happens, that's when acute effects are observed. And then in the third possibility is that the DNA is damaged. It is not repaired, but the cell can live. Now, if the cell is a highly differentiated cell, maybe a cell in the colon epithelium is going to live for another week or 2 and then be replaced by a new cell, and nothing's going to happen, except for those potentially for the short term of those couple of weeks of the cell functioning not very well. But if the cell is a stem cell, like those little cells that are at the bottom of the crypts in the colon and that are in charge of replacing the cells that are wiped out every week or every couple of weeks, then every single one of the cells that are made by that damaged single cell, by the damaged stem cell, has a DNA defect. And if that DNA defect is in some way associated with some of the hallmark of cancer development, this can accelerate the process of carcinogenesis, and that's where the connection between radiation and cancer essentially comes in as a chronic effect generated by a DNA damage and the acceleration of the carcinogenic process. Moving from cells to the entire human, this is a cartoon that illustrates some of the overall health effects of radiation and maps them to various exposures in terms of millisievert. A couple of points to make about this slide. One is that there are the long-term effects have to do with cancer, but not just with cancer. There are also cardiovascular, reproductive health consequences and others. The second is that the 1,000 millisievert, which is below what you would be exposed to if you were to participate in the Mars mission with the current spaceship technology, is already associated with a 5% higher chance of cancer. So this is where a discussion about how do we set limits to the amount of radiation that astronauts can be exposed to comes in. Before moving into that, a couple more slides. One is, we know some things about the connection between risk and cancer. We know it mechanistically because of the reasons that I described, but also we know it from epidemiological data, but there isn't a lot of it. And actually, most of the epidemiological data at doses higher than the ones that are part of the natural exposure that we're all exposed to come from at this point the long-term follow-up of survivors of the atomic bombing in Hiroshima and Nagasaki at the end of World War II. There have been other nuclear power accidents that are amenable to studying this type of exposure, and there are cohorts being built on that, but they're not as far along in terms of follow-up. And so much of what we know and most of the modeling is still derived from that. And this is a slide again from the Japanese website. Sorry for not including the credits to them, but I want to emphasize something in the footnote here, which is a major source of uncertainty in our projections of the risk from a relatively high level of radiation exposure. And it has to do with the fact that the atomic bombing event implied a large amount of radiation in a single bolus in time, while going to Mars would imply, even though the totals might be the same, if you're taking someone who lives far enough from Hiroshima, even though the totals might be the same, the exposure is happening over a long period of time. And I mean, you can, keep in mind that the main mechanism is making individual cells more prone to cancer evolution. And keep in mind that cancer evolution very seldom, except for a few varieties of leukemias that are associated with certain translocations and so on. But if you're talking about point mutations, for example, very seldom are they the result of a single mutation. It takes multiple mutations for these to happen. And so logic would suggest, I think, and here, if you disagree, let me know, but logic would suggest that a single dose has different implication from multiple doses, because if you have a single dose, if you need to, if Christian Tomasetti is right, and we need 3 on average mutations to get a normal cell into a cancer, a single exposure will have to get that 3 mutations in the cell all at once. But if you have a protracted exposure, you can get that mutation in, multiply the cell, and then you have many more targets for getting that second mutation that would get you the new hallmark and get you closer to being cancer. And then that would multiply perhaps as a result of the carcinogenicity of the first 2 and make it easier for the third one to occur. This is very similar to COVID variants, but we will not get into that digression. So, but as a result of this, it seems to me that extrapolating much of what we know about risk from the atomic bomb survivors cohort is a major challenge. With that major caveat, this table gives you a sense for the various estimated risks in terms of relative risk now for exposure to various amounts of radiation. The radiation doses on the left and the risks are on the right. Okay. A little bit of jargon here. This is something that NASA uses, and I think it's fairly common jargon in the radiation exposure world. The key word for you to remember is READ. It's the risk of exposure-induced death. And it's an absolute risk. It is essentially the difference between the risk, the lifetime risk, so the risk of death caused by cancer in the presence of the exposure minus the risk of death from cancer in the absence of the exposure. And the RIIC is the risk of developing cancer. But most of these standards are set in terms of the of exposure-induced death. So NASA thinks very hard about this problem, and they have a complicated model to figure out these reads and set their standards, which are called PELs, permissible exposure limits. This is a cartoon that gives you a sense for how many different sources of information have to go into estimating age and sex-specific risk as a function of the amount of ionizing radiation received over the course of a certain amount of time. On the left, you have the epidemiology side. I love it that they call it terrestrial epidemiology, but it is in contrast to the data that they have from astronauts in space. And the incidence of cancer among astronauts is certainly not high enough, and the number of astronauts that have been in space to do a direct study where you could do a dose response from space exposure in people who have actually been in space. So most of the terrestrial epidemiology is, as I said, atomic bomb survivorship. Then they obviously extrapolate. They have to use a baseline population data to make projection and make things specific to individual cancer type, and also to adjust for covariates. This is an important adjustment for covariate that they need to do, because the astronauts are healthy people. If you smoke, you're not allowed to be an astronaut, for example. There's an age range as well. These guys are fit. They are very well followed in terms of their health care and all that. So they're definitely not you know, you wouldn't draw the risk of dying of cancer from the average curve in SEER. You need to adjust it a little bit. And all the way on the other side, there are aspects of the modeling that have to do with what happens in space, exactly what type of radiation is present. Is this radiation quality factor? I love it that they call it quality factor. It means, how bad it is. It's the quality factor is some mysterious adjustment that has to do with converting the radiation that one gets into the equivalent of a gamma ray, which is their kind of baseline modeling. And then there are a couple of other aspects of modeling. This is a dose response model at the top, and there are other modules that remain a little bit mysterious to me, so I will not even venture into it. And then this is all put together into a model that measures the excess risk from gamma exposure and gives you age and sex specific risk. Now I want to pause for a second and ask you to think about this. This is a collection of 7 black boxes, but I want you to think of it as one big black box for a second. And this black box in each of these various modules has parameters. And these parameters have estimates that come from various places: mouse data, the Japanese cohort, physical estimates of the amount of radiation that would get into the spaceship. All these type of things are estimated. So as the input to this model, you have a laundry list of Greek letters. And NASA has gone ahead and figured out an uncertainty for each of these and model that uncertainty in a very Bayesian way through some probability distribution. Now, if you plug in your best estimates, you get a best estimate of age and sex specific risk for a given dose. Okay, so that's what the black box does when you turn the crank. Now, if instead you were to draw from the distribution of each of the parameters and generate a whole bunch of random laundry lists and redo the exercise for each, you get a distribution of the read for the specified dose, age, and sex group. You with me? This is important because this is the uncertainty about risk part. The uncertainty about risk part comes from this. NASA produces an estimate of risk and a distribution of that. And in the old version, it used the whole distribution to set the permissible limits for astronauts. Let me give you an example. This is something, by the way, that engineers and also a lot of people in the medical decision-making / decision analysis community for many years have called probabilistic sensitivity analysis, and you might be familiar with that term as well. That's what we're talking about. So the results look like this. Where am I? Yeah, let me go right here. This is the result of a probabilistic sensitivity analysis at some level of sievert for some profile, and you can see that it's in the scale of reads, and you get a distribution. So exposure, gender, and age here are fixed, and the uncertainty is from that exercise of drawing from the input parameter distribution. Now let's take a look at how NASA used to set these permissible limits for astronauts. And let's parse the sentence at the top. It says that planned career exposures to ionizing radiation shall not exceed 3% read, 3% risk of exposure-induced risk. This is an absolute difference between the risk of dying of cancer that an astronaut would have if they never flew, with the risk that they have if they fly for their whole career. And that sets the limit for their career exposure. That 3% is generated by the model that we have discussed or seen the overview just a minute ago. But then if you continue seeing, looking at this sentence, it says at a 95% confidence level. So what they are referring to here is the 97.5th percentile of the distribution of the probabilistic sensitivity analysis. So going back to the previous picture, this corresponds to some sieverts. You can ask the question based on this picture about whether this amount of millisieverts is admissible as a limit for an astronaut or not. And the way you would answer that question in the old NASA approach would be to look at the 97.5th percentile of that distribution and see whether or not it is above 3. In this case, this is below 3. So an astronaut that is at that level still has some brownie point and could go on another mission, perhaps a short one, but they still have not reached the permissible limit. This is not their best estimate of risk. It includes this consideration of uncertainty and in my view anyway, a somewhat arbitrary choice of the 97.5th percentile of this distribution to represent the point where to set the limit. Let's see this in action for Mars for a second. In the sort of bar chart at the bottom, let's start at the left. You see ballpark estimates of mortality risk for, say, an average American, about 20%, for an American smoker, about twice as much. For an astronaut, it's down to 15% because they're healthier people. For someone who would be going to Mars based on their current estimates of the amount of radiation they would be exposed to, the bump up is about 3%. It goes up to 18% as a best estimate, which happened to be right on at the limit of what the old guidelines would tolerate. But then the old guidelines were formulated in terms of the 97.5th percentile, and if you look at that, the estimated the value of risk associated with that goes up to 27%. If you now try to back solve the 27% in terms of the maximum exposure, you don't go to Mars. So that's pressure point number one for this report. NASA wanted to consider whether this approach was reasonable and was still serving them well, in part for that reason. Um, there's also another aspect of this that we're going to discuss in a second, and it is that if you were to do this picture for men and women, you would get two very different results. We'll get into the reason why, and that's a second pressure point for NASA, because the question of gender equity about their regulation had been raised both internally and from the outside. The third pressure point comes from sort of the commercial side of space travel and the things that you see going on in the news, and the notion that NASA should really set standards that industry can look at for private space flight in a way that is robust and reproducible and sensible and so on. So that's what we were essentially before the report that the national academies have produced. So NASA was not so happy anymore with this 97.5th percentile story, and so we were asked to evaluate the question of whether the limits should be set on a best estimate or on this quantile. And I'd be interested in maybe if people want to give their opinion about it in the Q&A or the chat. I'll give people a second to weigh in on with their thoughts on this. One of the aspects I struggle with is to interpret the estimates. When you have an estimate of risk, you think of a population, and if your risk is 7%, you think, I'm part of a group of people that for whom, if it followed over time, 7% would experience the event in question, and 92% wouldn't. And when I do a best, if that 7% is my best estimate for this population parameter that consists of an hypothetically infinite population of individuals with exactly these characteristics, I'm struggling a lot more to understand whether an interpretation like this exists for a quantile, because the variation in that quantile is the variation that is driven by the probabilistic sensitivity analysis. Some of those parameters may have some population-based interpretation as confidence intervals, but the majority are established based on expert judgment about how much uncertainty there is on different knobs in that complicated engineering machine that whose cartoon I showed you earlier. So that's a point for reflection. Is the population parameter interpretation important to us for absolute risk, important to us in trying to understand the limits? If you want to limit your risk, and there is uncertainty about that risk, should you still use your best estimate but have a more conservative cutoff on the best estimate, or should you pick some quantile to kind of compensate for that uncertainty? Have there been astronauts who have gone over their limit? Well, that's a really good question. There are astronauts that have gone over their limits, I believe, because the data that I showed you earlier was data by mission, and many of those astronauts went on many missions. And NASA always has the ability for national interest. There's some terminology that they use that we might come across later on, but they have the ability to have an appeal process, and if the astronaut agrees and NASA thinks that individual is the best person for the mission because of whatever experience they have, they can send them up in space anyway. So there have been examples like that in the past. Yeah. Anyway, back on conundrum on best estimates or quantiles. The pressure for NASA was to think about it in a slightly different way, and in the end, we ended up both NASA and the panel suggesting that the best estimate is maybe a better approach. One reason is the interpretability, and that's what I was alluding to a second ago. A second reason is that if you go back to the histogram that I was showing you, the distribution of the reads coming out of the sensitivity analysis is very, very skewed. And what you're doing is you're setting a limit at 3 at 3 in terms of the risk, and then you're reverse engineering how much exposure is you can tolerate before going there. But you can imagine that very small movements of the exposure could cause very small movements in the mean and the median, but whack the tail or wag, I suppose, the tail pretty wildly at the end. And so that degree of sensitivity is one that the committee was somewhat concerned about. Those concerns were compounded by the fact that NASA's model is just one model, and the sensitivity, the probabilistic sensitivity analysis is just one set of distributions. It makes one set of assumptions. It makes a bunch of independence assumptions, for example, of among all the parameters that go in as the input, which may or may not be appropriate at all. Interestingly, NASA is very receptive to this type of discussion, and they went and did a very, very cool ensembling project. And I want to give you a couple of slides on that. So what they did is, essentially the idea is to quantify visually and otherwise the model uncertainty around this curve. Now, we're talking about risk, so uncertainty about whether you'll die of cancer. Then we're talking about probabilistic sensitivity analysis, so uncertainty about risk. This uncertainty depends on the model, and so NASA went the step to the third level and tried to quantify the uncertainty on this distribution. And so here's the result of what they did on the left. Their anchor model, which is the one that you just saw a moment ago, is in black, and then they have a whole bunch of other models that they have tried out, which each has a curve in gray. They point out that if you look at summaries like the mode or the median or the mean, the variation across models is modest, and it does not have a very big implication on where you would set the limits from astronauts. But the variation that you get in the tail is pretty wide, and you get a better sense from that from the curve in the right when you're trying to invert the CDF essentially to try to back solve for the amount of exposure. So the 0.97 percentile could correspond to a risk anywhere between 1.59 and 5.15, depending on the models in the ensemble. And these could correspond to very different levels of millisievert limit when you do the inversion. So this is something that was that the agency was not very comfortable with, and that sort of contribute conspicuously to the final their final proposal to move to the mean, and the committees and the NASA committees sort of adherence to that proposal. Just want to say a couple of words on how they did it. You might remember from the way they constructed the model that they had 7 different modules. There are alternative proposals in the literature for many of these modules. So they boil it down to 4 components, and for each of those 4 components, they took various models in the literature. Their anchor model is NSCR 2020, and if you take a combination of each of those 4 components, you get their model. But then they have alternatives for each of those 4 components that they fished from the literature and implemented. And these paths are nothing other than just pointing out all the possible combinations that you can look at. Each each combination of these models give you a different type of prediction, and that's how they did the ensemble learning bit, which I thought was quite cool. Each model comes with its own parameters and with its own distributions for doing the probabilistic sensitivity. The paper on this, I think I put the link in the chat. It's a fun read. Okay, so I think I'm done with the mean versus percentile discussion. It lands NASA in a place that is much more similar to what the rest of the world does. This is a slide that summarizes the situation right before this change, and you can see that Canada, Europe, and Russia all have a career dose limit at 1,000 millisievert, big round number, end of story. The Japan and the US use the NASA model for setting the standard in terms of risk, and then they back solve for the millisievert. But Japan, even before this move, was already using a best estimate, while NASA was doing the 95% or the 97.5 percentile story. They call it a confidence interval. It's a little bit confusing. Now, this is also a good intro for the next bit of the story, which highlights the fact that in both the Japanese and the US version, the career dose limits are very different for males and females. Why is that? I don't have a ton of time, but this is a slide from the NASA 2012 model, and it contrasts males and females. You have four columns. You're looking at lifetime risk of cancer as an absolute risk, and each pair of columns. This is pair number 1, this is pair number 2, compares males and females. And most of the differences are coming from lung here, and here for breast versus prostate. And here, this shouldn't be rocket science, but evidently it is. The scale here goes all the way up to 6, while for prostate, it's a 6%, and for prostate, it goes to barely 1 percentage point. And so that's another big gap. So how much uncertainty there is on this gap is another whole can of worms, because many of these estimates rely on the atomic bomb survivors, and it's been a very controversial point about whether or not women are more susceptible than men to lung cancer when exposed to ionizing radiation. And there's another panel of the National Academy that is deliberating on this very point as we speak. So this whole the gap between the two estimates might be substantially reduced in the future as new evidence is accrued. But for now, these are the estimates that NASA uses. So to move beyond this, the committee proposed to adopt what was described as the most vulnerable group approach. And essentially, you pick the most vulnerable group, in this case, a 30-year-old female. You set the risk for that group, say 3% read, and then look at the limit in terms of millisieverts that group needs to be under to control the risk. At this point, you apply this limit to all astronauts. So the risk is now, the limit is now the same amount of millisieverts for all astronauts groups. It's established based on protecting the most vulnerable group, which in this case happens to be young women. So this is a substantial change. It brings the US rule to something a lot more similar to Canada or Europe, where except that instead of 1,000, it turns out to be about 600 or so. What is the justification of the logic behind this? The idea here and you may buy it or not, but it's at least compelling to discuss, is to ensure a minimum level of protection for all individuals involved. So that's the principle. A byproduct of this principle is that it levels the playing field in terms of opportunity for participation in missions. If you remember the slide where I was showing the limits for males and female astronauts, it was like 4 times as much. So men could participate in missions that would total to a radiation exposure of about 4 times as big, because of the belief that they would be at less risk, mostly as a result of the lung cancer. Yeah. So the playing field is now level. On the other hand, if the gender difference risk is real, women would incur a higher risk. That is, males would derive a greater protection. They would stay in a risk range that is much more comfortable. There's no way around this dilemma where you have to compromise one way or the other. But this is quite an interesting dilemma in my mind, and one that I've come to view in a very different way as a result of the work with this panel. There's a question from Jill about tolerance interval, and I must admit that I don't know what they are, so I'll try to save a couple of minutes to the end in case she wants to expand a little bit and teach me enough that I can say something cogent about it. Okay, a few seconds on the new guidelines and on the risk communication. The final approach that NASA landed on is this famous or infamous traffic light approach, where there are 3 levels of risk associated with 3 different types of risk management and risk communication. At the bottom, you get a generic risk assessment, which means that you're communicated. You are told that your risk is below a certain level, and that it does not warrant any individual discussion. Then once you reach 300 millisievert, but you're still below the 600 millisievert limit, you start getting into the yellow area, and you receive individual assessment. As part of the individual assessment, your risk begins to be stratified by age and gender. So if you are a woman, you're learning that you are at a higher risk than if you're a man. And you also learn about the infamous uncertainties in the sensitivity analysis. The astronauts are very quantitative people, so there's a high level of comfort in sharing that information, although it's really unclear how they would want to process it as part of their own decision making. And then the 3rd level is above 600 millisieverts, which will require the agency waiver, which is the correct terminology for the answer to the question that I was asked earlier on. The waiver can be given for national imperative considerations. I tried to explain earlier what that means. So that's where we landed. I have a couple of questions in the chat, so I want to jump to those. Yeah, Jill, let's take this offline. We have 1 minute left, and I have never encountered the terminology tolerance interval, which only speaks to my vast ignorance just about anything. But sorry, I'll have to punt on that question. I won't get into this either. These are the links that are in the chat. And with that, we're at the top of the hour.
Anyone has questions, please send them to the Q&A. That's the last call. But overall, this is extremely interesting and extremely exciting. I was thinking that, like, one of the challenges is indeed that there is not too much observational data, and one can imagine that the exposure, terrestrial exposure, must be very different, because with the nuclear catastrophes, what happens is also you have a lot of surroundings contaminated. So there's a lot of the radioactive metals in the food and in the dust around, which is not necessarily happening on the missions. And arguably this is more dangerous when something is inhaled or ingested rather than just like pure ionizing radiation. It's more that having this ions incorporate into thyroid and other that kind of keep exposing you.
Yes.
Yeah, so that's
That's very true. That is a very reasonable point, and I wouldn't be able to judge the extent to which these uncertainties are incorporated in their modeling at this point. You are right that if although it's true that for evolutionary reason, I believe it's reasonable to make the assumption that the one-time exposure is a lower bound. It also has implications for the environment that could create bigger exposures and turn out to be an overestimate in the end. Point taken. Point taken. Yeah, very good point.
So there is a link, the link to the nasa.gov. They say it doesn't work. I think what we could do, maybe we can also have the references and maybe they can be distributed and they will by email or.
I'm sorry about that.
It's probably the special symbols that gets messed up because you know this like %5.
Oh no, you know what I did? I copied it from the tech document and I had replaced the underscore with \_.
So that should fix it.
That's fixable.
Yeah. All right. Well,
fixable
I don't.
And testable. Let me see. Okay, I plopped it in the chat now and tested it, and it works.
All right. So we probably are all set then with links, and there doesn't seem to be more questions. I guess it requires some additional food for thought to think, outside of the box. And I guess if we get anybody gets thoughts, please contact Giovanni, I suppose.
Of course, always happy to discuss.
Well, I guess then we can close. And thank you very much, Giovanni. It was very interesting, very educational. And hopefully we will sometime in next year or so with more developments, we will be happy to hear more about it. Thank you everyone for joining. Bye.